So, Professor Klingler will give the second lecture of his series of talks on Tame topology.
Thank you. Okay, so yesterday I started explaining applications of Tame topology. So let me continue this. So maybe I will just recall the statement. It was application to complex analysis. And the main result was the following theorem by Peterzin and Starchenko. Which was saying the following, that if you start with X, which is contained in the complement of a C-analytic set, in S, which is also C-analytic and definable, and by definable I mean definable in some omnimal structure, and suppose that X is also complex analytic and also definable in the same omnimal structure, then this implies that X bar, the closure of X in S is complex analytic, and the dimension of X bar is the same as the dimension of X. So this was the main extension result for those definable sets which are also complex analytic, and as a corollary we had this definable Chow theorem, stating that if you start with X inside S, and this one is now complex quasi-projective, and X inside S is a complex analytic and definable in some omnimal structures, then X is algebraic. Okay, so it was just to remind you the main result of that I stated at the end of the lecture yesterday. So what I want to talk about now is application to Diophantine geometry. So of course, I'm not giving any proof of this kind of results, this kind of a survey, but I think really these two ideas that this extension theorem for complex analytic sets, which are also tame, and the application that I will describe to Diophantine geometries are really the two main tools that have been used in the last 10 years very efficiently in different areas, and I will review the areas after that. So what is the idea? Well, what is usually Diophantine geometry? Well, you start with X, an algebraic variety over Q, or Q bar. Let's say Q, for simplicity, or a number field K. And the goal of Diophantine geometry is basically to understand, we would like to understand the geometry of the rational points. Geometry. Like the distribution, the density properties, and so on. And what is amazing in this use of Tame topology is that in some sense, you completely reverse the perspective. So omnimality reverses this perspective. This means that in a classical context, you start with something algebraic, and you deduce something about the points. And here, on the contrary, you start, you create, if you want, algebraic sets from rational points. So let me explain this. I will need to recall the classical notion of height. So what is a classical height function? Well, you start by defining it over Q. Just that if you take a rational number A over B, where A and B are relatively prime, then you associate the max of AB. Okay. You are just measuring the complexity of your rational number. So you extend this to Q to the N. Just component by component. So take the max over each component of the height of your rational numbers. And now I can directly state the main theorem, which is really, in my opinion, a fantastic theorem due to Pila and Wilkie. We just say the following. So suppose that I start with a definable set inside R to the N. So I repeat, definable means definable in some or minimal structure. Then you can define the algebraic part of X as being the union of connected positive dimensional semi-algebraic subsets of X. And now your problem is to be able to say something about this part. A priori, if you start from some definable guy, it could well happen that there is no it does not contain any positive dimensional semi-algebraic set. And so the theorem tells you the following, that for any epsilon larger than 0, there exists a constant depending on x and epsilon, such that if you count the number of rational points in x minus the algebraic part of x intersected with q to the n, whose height is smaller than a constant number t, then the cardinal of that set is smaller than this constant depending on epsilon, t to the epsilon for any epsilon. So in other words, so let me just give so this is a quantitative, a very precise quantitative statement, and the moral is that if x contains, is definable and contains a lot this is a qualitative statement, and the quantitative version is just above, contains a lot of rational points, then in fact X contains a positive dimensional semi-algebraic set. So let me give the most trivial example of this result. Suppose that you start with the box 0, 1 cross 0, 1. And now you just take a curve which is real analytic, restriction to that box of a real analytic function. Okay. So now, so you are in that box. So this means that this set is definable in the structure Rn that I defined yesterday. Now you count the points on C which are in Q square. So suppose that this point is lies in Q and also, okay? You count the number of such points of height smaller than T. If you manage to prove that there are at least T to the power epsilon for some epsilon, whatever, then you know that in fact this curve is algebraic. So if C intersected with Q square is large, then C is algebraic. Real algebraic. Okay. So I won't give any idea of the proof of this. In fact, this is some kind of elementary analysis. But what I want to explain now are applications of those two kind of things, and especially this theorem, to questions in functional transcendence. Basically, O minimality has been used to prove results in functional transcendence, and those results are used, for instance, for proving Manin-Mumford conjecture or Andreaert conjecture. So I want to give you a glimpse of this. It will be interesting to have a kind of general setting, because it will also apply tomorrow in Hodge theory, in the next lecture, not tomorrow, for the Hodge theoretic stuff that I want to explain. So the general setting will be the following. You start with S quasi-projective over C. So of course, I identified the quasi-projective variety over C with its complex analytic points. Okay, I will not make the difference. And I will denote by pi the universal cover of S. Of the analytic space associated to S. Okay, and then it's kind of a strange thing to do for an algebraic geometer, because usually that guy has no algebraic structure as soon as the fundamental group is infinite. So usually, as soon as pi1 of x is infinite, S tilde has no algebraic structure. Nevertheless, you have to observe that it has been a long tradition in algebraic geometry, in complex algebraic geometry, to study algebraic varieties through the universal cover. I mean, it was done by, for example, elliptic curves by Euler, for abelian variety by Abel, or for Riemann surfaces by Riemann. Okay, so it's a very efficient tool, even if you get out of the category of algebraic varieties. And the idea is that you would like, in some sense, to force S tilde to have an algebraic structure. So, so what is the goal of bialgebraic geometry? It's not such a nice name, maybe, but I think it will be clear. So the goal is to emulate an algebraic structure on the universal cover. So by this, I mean the following. This will be the following definition. So you look at your universal map, your uniformization of S tilde, and a bialgebraic structure on S is the following diagram. You give yourself just a map F from the universal cover S tilde to X, where X is algebraic, F is holomorphic, and now you want to relate this to S. So this means that it has to have an equivariance property under action of pi1. Pi1 of S equivariant, and some morphism H from pi1 of S to the algebraic automorphism of X. So, of course, you have exceptions, but take a random Riemann surface, and the universal cover is H, Poincaré upper half plane, which is not an algebraic object. But you notice that it is almost. It is semi-algebraic. Okay. In fact, there is a conjecture by Collar that if you take a smooth projective variety and its universal cover is naturally algebraic, then in fact this universal cover has to be a product of C to the n cross a projective simply connected variety cross not so much in fact. Basically this is it. Yes? Yeah, so the lot just means that you have to be able to, yes. I will explain, I will give an example where I will really prove use such a. Yes, and the place where you count points is not the manifold itself, but it's in the group acting upstairs, and this is where you count. Then you have more structure. Okay, so the idea is that in some sense, X is the algebraic model of S tilde. And of course, it has to be related in some way to S. And the relation is just to the mild fact that this map is equivariant under pi 1. And for the structure to be interesting, you ask that the image of the monodromy is infinite, with infinite image. Because otherwise there is no sufficient link between this map and S. So let me give some examples, very simple examples. And in the next lecture, we'll see more non-trivial examples. Sorry? No, this is true. So you will see that in the basic examples that I give, the map is always an immersion. But in fact, in Hodge theory, it does not have to be. Yeah, I'm not saying that there is a general theory. I'm just saying that there is a general picture, and then each time you have to prove really what you want. But okay, so the first map will be the following. This is a multi-exponential, 2 pi I. So this constant is not needed for what I explain now, but it will be needed later. So it's just the uniformization of, so S will be C star to the n, and the universal cover is S tilde, is C to the n, and just a classical uniformization. Okay, a second example is the case of abelian varieties. Well, in this case, just notice that the bialgebraic structure is kind of trivial, right? The universal cover itself is already algebraic. So the map F is just the identity. So I do the same for abelian varieties. Then more interesting, you can do the same for what is called arithmetic varieties. So let's give the simplest example. You take the modular curve, right? So S will be y0 of 1. Which is the quotient of Poincaré upper half plane by PSL to Z. And the diagram that I'm looking at there is just the usual one. Okay? And this map is equivariant under the action of PSL to Z, seen as a subgroup of PSL to C acting on P1C. More generally, you can do this for any Chimois variety, or let's say arithmetic variety. So more generally, you can look at S, which is what I call an arithmetic variety. So D is a bounded symmetric domain in C to the n, if you want. And then it's canonically embedded in a flag variety. Which is its compact dual. And gamma is an arithmetic lattice in the group of automorphism, or biautomorphism of D. Okay, so such a guy is called an arithmetic variety. Okay, so these are trivial examples of these bialgebraic structures. These have been the most studied ones. So now let me explain, once you have this notion of bialgebraic structure, why this is interesting. So the first thing that I do is I define what are algebraic subvarieties of S tilde. So you have fixed your bialgebraic structure, and then I will say that an irreducible analytic, a complex analytic, irreducible subset of S tilde is algebraic if it is the preimage under F of something algebraic. In other words, if it is of the form F minus 1 of what? Well, of F of V zar. And then you take an irreducible component. Okay, so this is an irreducible component of the preimage under F of something algebraic. And now I define what are the bialgebraic subvarieties of S. So suppose you start with an algebraic subvariety of S, then which is also irreducible. We say it is bialgebraic or weakly special, if you want. If one, or equivalently any, irreducible component of pi minus 1 of y is algebraic in the sense above. So now we have our main player. What I'm interested in, I mean, in some sense, I'm playing the algebraic structure of X against the algebraic structure of S. Of course, usually this map will never be algebraic. So what I'm trying to study are the transcendence property of that map. And I'm looking at the sets here, which by accident happens to be algebraic already upstairs. And these are the bialgebraic sets. And what I want to convince you is that this collection of subsets, they really understand a lot of the geometry of the situation. Maybe, even if I don't want to spend too much time on this, this situation can be refined to deal with the case of points. Because notice that with this definition, any point is bialgebraic, right? So we refine the situation as follows. Well, you refine over Q bar. You have the notion of Q bar bialgebraic structure. So maybe I will not rewrite, I will just say it with words. So you look at that diagram, and a Q bar bialgebraic structure will be the following. You ask that S is defined over Q bar. Maybe I can just put some. That X is defined over Q bar. That it takes value of the automorphism over Q bar. And that's it. Okay. And then what No, it's really an irreducible component of the preimage, not an open irreducible component. This 0 means irreducible component. So if you look at this refinement, then you can define the notion of Q bar bialgebraic, and these ones I will call special. And now there is a notion of Q bar bialgebraic point. So this is a point of S defined over Q bar, such that it is the image of a point defined over Q bar in S tilde, in the sense that I defined, okay? So now you also have a nice definition for points. Q bar bialgebraic points. Okay, so let me try to illustrate those notions to convince you that they are of interest in the examples that I gave. So in example 1, so you have pi, which is this multi-exponential, and the 2 pi l will be used for the Q bar bialgebraic structure. So the lemma is the following, that y in C star to the n is bialgebraic if only f y is a translate of a C star to the k contained in this torus, a subtorus. translate of subtorus. So you see that in some sense, in this example, the bialgebraic structure recovers entirely the group structure. And the next lemma, so this is easy, it's a good exercise. Here I'm writing lemma. If you are not used to classical transcendence theory, this is not easy at all. No, you have only this. Okay. So I claim that a point in C star to the n is bialgebraic if and only if it's Q bar bialgebraic, if and only if S is a torsion point. Oh, I'm late, okay. So, and this is really a transcendence result. This is Gelfand-Schneider theorem. And this is where the constant that you put in the uniformization is very important. If you put 1, then in fact there is only one Q-bar bialgebraic point, which is the identity by Lindemann's theorem. Okay, so usually when you see this kind of constant, this is of no interest for the algebraic part of the definition, but this is of crucial importance for the arithmetic part. Okay, let's do the case of abelian varieties, and you can already guess what happens. So you have this uniformization, where this guy is basically C to the n, okay? So this is my abelian variety. And this time this is really a nice exercise about the universal property of Albanese morphism to prove that if y is in A is bialgebraic, and this is the same thing as saying that this is a translate of an abelian subvariety. Okay. Now, this is tricky. So if A is defined of a Q bar, then in fact you can arrange to put a Q bar algebraic structure on VEA such that this result is still true, such that the Q bar bialgebraic points really are in bijection with the torsion points. And once more, this is not the trivial algebraic structure. Right? I mean, if you start from A defined over Q bar, VA is canonically the Lie algebra. And you could take this Q bar algebraic structure on the Lie algebra. If you take this one, you have the same problem as here, that you get only one Q bar bialgebraic point, which is the identity. So you have to be much more tricky. You have to really take the lattice of periods to define the Z structure on that guy. And then in that case, basically, these are results due to Lang and Masser that you can do this. Okay, let's move to the case of arithmetic varieties. It's still on the board, so it's nice. So I'm in this situation. And then the proposition due to Ulmo and Yafaev is that y in S is bialgebraic for this structure, if and only if you want, y is totally geodesic for the canonical locally symmetric metric that you have on that space. And in the case of abelian varieties, this characterization of bialgebraic sets was a universal property of Albanese map. Here, this is the linear semi-simplicity theorem, essentially. So, and then there is the following theorem, if you are now interested in the Q-bar bialgebraic structure. Well, here, this guy is canonically defined over Q, so that's even better, and it's well known that any arithmetic variety is canonically more or less defined over a number field. If you are in the Shimura case, this is strictly true in the sense that this is a reflex field. And then the theorem due to Cohen, Paula Cohen, Shiga, and Wolfart. Well, in fact, we don't have a full result, but we have a result in the case where this Shimura variety is of abelian type. So suppose S of abelian type, for example, the case S is AG, a moduli space of principally polarized variety of. Well, essentially, I mean, this is related to this Green's-Lazarfeld theory, yes. I mean, this is a different, completely different approach to this, but yes.
So, you understand that the Lafayette theorem, it's an older result stated differently, but you are restating it in the dimensions.
And it's not another result, but the main ingredient is classical. This is this Deligne semi-simplicity theorem for variations of Hodge structures. This is all what I'm saying. I'm not. It was not written before, but the main ingredient in the proof is this. No, but it's true. They agree. Suppose that S is of abelian type, then a point is Q-bar bialgebraic or special. If and only if this is a CM point. By this, I mean in the case of AG that the point corresponding, the abelian variety corresponding to that point is a CM abelian variety with complex multiplication. So let me just give, of course, this is a generalization of the very classical case of modular curves. So in the case of modular curves, you are in this situation. By the J function, you identify y0 of 1 with C. And here, you are putting this, if you want, in Q-bar tensor C of Q. So this is just, what I mean is that here, this is just a stupid Q-bar structure that I'm putting inside P1C, if you want. And then the result is that you take a point in, so this is my S, in S of Q-bar, so this is really a point in Q-bar here. And what I'm saying is that this is a Q-bar bialgebraic. So this means if and only if there exists an element tau in H intersected with the Q-bar points here, so you are really in the upper half plane intersected with Q-bar, such that what? Such that J of tau is, which is my X, is in Q-bar. So you are just looking at points in the pointary upper half plane intersected with Q-bar, with image is also in Q-bar. And then this is a very old result of Schneider in 37, that in that case, if tau is in Q-bar and J of tau is also in Q-bar, this is possible if and only if J of tau is a complex multiplication. So tau is imaginary quadratic. Okay, so this is the main point. What I want to explain now is that O-minimality will be the crucial tool for proving results about this bialgebraic stuff. But I just wanted to give a general setting where you can try to apply to your favorite object these kind of techniques. And I will illustrate it more this afternoon. So what is the bialgebraic heuristic? The bialgebraic heuristic is that it's kind of geometrically easy to find what are the bialgebraic variety. It's usually hard, transcendence theory, to find the Q-bar bialgebraic points. And then what do you want to do with this? Well, the heuristic is that, this is a very general heuristic, is that suppose you are in this situation, and everything is over Q-bar. So it's a Q-bar bialgebraic structure. Yes? Well, basically because this is the only, it's only in the case of abelian varieties that you have the transcendence result that you need. I mean, if you take a Shimura variety of exceptional type, then basically yes, this is really non-trivial. This is basically, I mean, all the results I'm stating are consequence of Wüstow's analytic subgroup theorem. So suppose you are in this situation, and suppose that now what you want to understand is really the distribution of spatial points, of cubar algebraic points. Of spatial points. So I remind you that spatial means cubar algebraic, but it's shorter. Then the heuristic is that you hope that it implies that Z itself is cubar algebraic, namely spatial. So this is the heuristic. So if you apply this heuristic in the examples that I gave, these are theorems in all the cases that I gave. So this is Mahan in 65 for S being C star to the n. Right, so if you have a subvariety, irreducible subvariety of C star to the n containing a Zariski-Dense set of torsion points, then it is a translate of a torus by a torsion point. Okay, so this is Reno for the case of abelian variety, for the Manin-Mumford conjecture. Stating exactly the same thing. You have an abelian variety defined over cube bar, and you have an irreducible subvariety containing a Zariski-Dense set of torsion points, and this guy has to be a translate of an abelian subvariety by a torsion point. And then there are many authors. So Pilar, I did some work with Ulmo and Yafaev, and Pilar Zimmerman and Zimmerman alone for Shimura varieties of abelian type. So now what I want to explain is how you can apply O-minimality to this kind of stuff. And basically, O-minimality will deal with the geometry of the situation through a functional transcendence statement. And this functional transcendence statement is what I call the Axe-Lindemann heuristic. It will say the following. You are in the same setting. Suppose that you start from something. It's a very nice, clean algebraic statement. Suppose that you start with someone which is algebraic in the sense that I define in the universal cover and irreducible. Then what you can do, you want to study its projection. So pi is only analytic. So usually this guy is completely disgusting, right? I mean, you have an infinite cover and you take the projection of something algebraic. So you cannot say anything about that, but you can study the Zariski closure of this. And then the result is that this guy should be bi-algebraic. So of course this is a heuristic, and this is Axe for C star to the n, and the case of abelian varieties, and this is Pilar Zimmerman and myself with Ulmo and Yafaev for Shimura varieties. Of abelian type, inside basically the one that you can embed nicely inside AG. Okay. So essentially those which are really moduli varieties of abelian varieties with extra structures. Because otherwise you can get moduli spaces of some one motives, and then you're, some things not so nice. Some things that we don't know really are some things that you don't really know if there are moduli spaces of nice algebraic structure. Because you have Shimura varieties, for example, associated to group of exceptional type, this kind of stuff. And also some orthogonal types that cannot be embedded inside. So this is a heuristic, and this heuristic was satisfied. And so what the point is that what I claim is that O-minimality is the main tool for proving this. And basically, This first part of the heuristic, well, this is axiom domain plus property of Galois orbits of special points. Sorry? Special points, as I said, is the same thing as a Q-bar by algebraic point. Sorry. It's just because the terminology, I mean, this terminology of special points was introduced before, and in our setting, it should be called Q-bar by algebraic, but it's not very nice. So I would say, so the general picture that you have to have in mind is that this one should follow from this 2 by 2 plus size of Galois orbits of special points. Basically, and here there is some minimality, but I will not explain this. What I want to explain, or maybe I will give an example, in fact. So now what I want to explain is that here 2 is implied by what I said about minimality, and it also enters here. So yes, yes. So in fact, in this strategy, we use 2 times this kind of pillar result. Once here and once from this to this. So crucial in this approach is that you want to be able to apply minimality, and so you have to be in a definable context, of course. So what you want is that if you look to this, is that this map has to be definable in some minimal structure. This is a basic requirement, so you want this. You want that the uniformization is definable. Of course, this is not possible because periodic maps are never definable in some minimal structure. But the trick is to go through a fundamental domain. So what you want is that there exists a fundamental set inside S tilde. So fundamental set for pi1 of S, which is definable, and such that the restriction of the uniformization map from F to S is definable. If you have this, then you are in business. You can apply the minimal techniques. So this is clear in all the cases that all the examples that I gave, and this is even true in R-alg. So for abelian varieties, this map is the identity, and so this is trivial. And same for tori, and otherwise, for the case of Shimura variety, S tilde is semi-algebraic inside something algebraic. So this is clear too. This is trivial in the case of tori and abelian variety. In the case of Shimura variety, interestingly, this is the theory of Siegel sets. The fundamental set that you will take is a Siegel set. Okay, so I should have such that, I should have put another point. And what is hard is this. The fact that if you restrict to a fundamental set, this map is definable, then in the case of Shimura variety, this is really hard. What I can do is give you an example of what happens. What time is it? Well, yes, I can do that. So let me just give an example of the last point. So maybe I will call this A, B, C. Example of C in the case of modular curves, just to give you an idea. So you're in the case of modular curves, so you start with that map. So here the theory of Siegel sets is very classical. You have even a fundamental set, which is well known for the action of SL2Z on H, which is given by the usual picture. Sorry, -1, 1, and then. So you have this half circle, and above minus 1/2 and 1/2, you have this strip. Okay. So this is your F parameter set, and this set is clearly definable inside H. So now the question is, you want to prove that the map from F to this guy, which has been identified by the J function to C, is definable in some omnimal structure. This is what you want to prove. Now, what you know is that the J function will factorize as follows. Here you can apply exponential 2 pi I z, that you write as being exponential minus 2 pi I y, exponential 2 pi I x, minus 2 pi y, sorry, exponential 2 pi I x, okay? So if you look at this map, then you are going to delta star, okay? Which you think of as being inside delta. And now this J function will factorize through that map, through a map that we'll call J bar. So what I want to prove is that this factorization is definable. So now for the first map, it's more or less tailored on purpose because so this is definable in R and X. Definable in R and X. Why? Well, notice that we said that this map is never definable. It's essentially sinus or cosinus. But here, this is very different because X is between minus 1/2 and 1/2. So this thing is a real analytic function in restriction to a compact set. So this is even definable in Rn. And this one, by definition, is definable in Rexp. So the product is definable in Rn exp. Okay? And now the fact that this J bar is definable, well, this is basically the fact that the J function has a pole of simple order at 0. In other words, this map extends to a map to P1C. But then this is a complex algebraic map even, so this is definable. Okay. So this gives you, and of course this is a baby case of this in the case of few varieties, but the way we did it was using the full theory of toroidal compactification that in some sense exhibit exactly the same kind of charts where you have this picture. Okay, so now what I want to explain is really how to use ominimality in proving one instance of 2 and how one instance of 2 plus size of Galois orbits implies 1. So up to now it was a lot of words. Let's try to give really some mathematical content. So let me prove the axiom domain property for abelian varieties. Theorem, axiom domain for A, which is CG over some lattice, so for an abelian variety. There is another way of stating the axiom domain theorem. Axiom domain tells you that if you start from something algebraic upstairs and you project it and take the Zariski closure, then it is bialgebraic. But you can also state it this way. You start from something algebraic downstairs in S, you take the preimage, inside the preimage you take something algebraic of maximal dimension. Okay? And then this guy is bialgebraic. It's kind of an easy statement to prove that both are equivalent. So I will, and for the proof this is a much better statement. So you start from something algebraic irreducible. In your abelian variety, you take the preimage, and inside the preimage, you take someone which is irreducible, algebraic, and maximal for this property. Then the claim is that pi of y is bialgebraic, namely the translate of an abelian subvariety. This is what you want to prove. Okay, so I will not give the full proof. I will do the easy case where I assume that A is simple. So for simplicity, assume A is simple. Right. Then what I want to show that as soon as if pi of y is of positive dimension, so it's positive dimensional, then it has to be the full abelian variety. Then V is equal to A, this is what I want. Okay, so without loss of generality, when I do this, I can assume that pi of y, which is contained in V, is Zariski dense in V. If it is not, I replace V by something by the Zariski closure. So I can assume that pi of y inside V is Zariski dense. And so now, as I said to Claire before, what we want to study is not really y or pi of y itself, but the stabilizer. So enough to show that if I call theta y the stabilizer in C to the G of y, I want to prove that this guy is positive dimensional. So I'm just looking at the group stabilizing this maximal algebraic stuff upstairs. If it is positive dimensional, then V, which is the Zariski closure of this, has to be stable under the image of theta y, but also by the Zariski closure because it is algebraic. So it's stable under pi of theta y, Zar. But this guy is positive dimensional. It's a subgroup of a simple abelian variety, so it has no choice. It has to be the abelian variety itself. But then I would have proven that V is stable under the action of A, so it has to be A itself. Okay? So the only thing that I really have to prove is this statement of positive dimensionality of this algebraic group. Okay, let's do that. So what I do is I put myself in my conditions of applying a Pila-Wilke result. So I will just look at the set of Z in CG such that Y plus Z intersected with my fundamental set. So of course in a abelian variety my fundamental set is very trivial, right? Something like this, is non-empty. First, and of the same dimension as Y. And such that I plus Y plus Z, is contained in pi minus 1 of V. So I'm still in the preimage of my V downstairs. So if you rewrite it, you can see that this is a C in CG, such that the dimension of Y plus Z intersected with F, intersected with pi minus 1 of V, is equal to the dimension of Y. Okay? And so it is enough to show that this set, sigma y, contains a semi-algebraic positive dimensional subset, let's call it W. Because if I prove that this guy contains such a W, then by maximality of Y, then if I have this, then this Y plus W, by dimension maximality of Y, this guy has to be Y. Because essentially this thing is still algebraic, contained inside V. And so W has to be contained in theta Y, and so theta Y is positive dimensional. Now, I claim that this set is definable. Why? Well, this is something I didn't say here, but yesterday. But the dimension function is a definable function, and f is definable by assumption. This is trivial in our case of abelian varieties. V is definable, and so pi in restriction to F is definable by the previous statement. So this guy is definable. Translation is an algebraic operation, and so I'm done. So notice that sigma of y is definable. And so now I just want to count rational points. And to count rational points, in fact, I count z points. I intersect with the lattice. So this is a set of z in lambda such that y plus z intersected with f is just non-empty. So you see that at the end, what you are just counting the number of elements in the lattice such that when you translate y by this element, you still intersect the fundamental set. Okay? So it's a very simple counting problem. And the claim is that the cardinal of that set such that the height of the element is smaller than t, it is at least t over 2. And then if you have this, then by Pila-Wilkie you are done. Okay? So how do you prove this? Well, you just, in this case, this is very simple. This is quite different from the case of Shimoa variety. You just, because the geometry is flat, and this is really what you are using. So you just take any path in Y, so, and you choose it that this is unbounded. So this guy is contained in C to the n, the universal cover, unbounded in C to the n. And this exists because Y is algebraic, so it has to go to infinity. So you take a pair going to infinity inside Y, and then you can just count this thing, the set of elements in lambda, such that the image of this path intersected with F minus Z is different from the empty set. So this is obviously contained in the set you are interested in. But then I claim that this thing is from a set of consecutive integers and the reason is that the height, when you pass from one fundamental domain to another one, it can just decrease or increase by 1. So once you touch something and you go to a neighbor, then you can just, if you look at the height, it will just increase or decrease by 1. And so of course, so it's from a set of consecutive integers. So let's say as the height for adjacent z in lambda increases by at most 1 when z goes to infinity. Okay, but then I have this infinite set, and so it tells you that roughly speaking, so of course, I'm not very precise here, but this is essentially T, right? Because once you are inside your fundamental domain, then when you continue and you count an element, essentially you count exactly the height itself, okay? And so this proves the result. Maybe I will take 2 more minutes to give you the proof of Mahan-Mumford. Using this, so that you see how you apply the second time O-minimality. So proof of Mahan-Mumford. In the case where well, I will assume that V over Q bar, A over Q bar is simple. And I'm assuming that V is already defined over Q bar. And then I want to show, because my assumption is that this is simple, and I want to show that V contains only finitely many torsion points. Torsion points. This is a statement. So of course here I have to put a strict. Okay, so let's do the proof. A is simple, so it does not contain any abelian subvariety, a proper abelian subvariety. So by Pila-Wilke, for any epsilon larger than 0, there exists a constant C epsilon such that the set of Z in pi minus 1 of V intersected with F, such that the height is smaller than T is smaller than C epsilon T epsilon. So here we are really counting in C to the n, but notice that C to the n is essentially also the group acting on itself, right? So this is really where we are counting. So we know this by Pila-Wilke. So now if P is a torsion point, this means that P is of the form pi of Z and basically now you have to understand what is the height. Well, the height of this Z is the order of the torsion point. Okay, so to compute this height, this is the same thing as the order of the torsion point. So now we use the result of Masser. And this is where we use that A is over Q bar. So it tells you that if you look at the Galois orbit, so this is the field of definition, K is the field of definition of A, and it tells you that the Galois orbit of P is larger than C times T to the rho, where T is the height of Z, okay? Where C depends only on A and rho on the dimension of A, in fact. So I use this very strong statement about the size of Galois orbits. It tells me that the Galois orbit of a torsion point has to be at least a power of its height, or the order of the point, height of the preimage. So what does it prove? Well, I put this upper bound with this lower bound, I place them one against the other, and this proves that any torsion point, of course, I should say, because I'm assuming that V is defined over Q bar, if P is contained in V, then its entire Galois orbit is contained in V. So once I have one, I have many. So, so playing this upper bound by this lower bound, we prove that any torsion point on V has a bounded height, uniformly bounded height, smaller than some T0. But now it's a classical result that you have only finitely many such. And you are done. Okay, I'll stop here for today.